Okay, so what are linear relations? They are relations where the data values all lie on a straight line. Linear relations have a constant change in the independent variable that results in a constant change in the dependent variable. So think about a line, straight line. If you needed a ruler, would those points, if you had a ruler, would you be able to join them up with a straight line? So the graph of two relations are shown. Which of the two graphs shows a linear relation? Hands up for A. Hands up for B. Okay, it's A. Get a ruler out, a straight edge, it's A. B is curved, right? So it is not a straight line. So A, I'm just, oh, no, didn't want to do that. Didn't want to do that. I'm just going to circle it. Here's a sec. So that is the linear relation. Use the graphs above to complete the table of values. So now I want you to look at filling in the table of values from the points. We now know this from the last unit, or you should know it from before actually. So when the number of guests is 0, the cost looks like 400. When it's 10, it looks like 900. When it's 20, it looks like 1400. Okay? Do that for both sets of graphs. So I'll give you a minute to do that. Okay, so if you take a look at relation A, for every change in 10, so these are all increasing by 10. Doesn't have to, but that's just what we've put in our chart. All of those are increasing by 10. I'm just going to make this skinnier here. These are all increasing by 500. So that's saying for every increase of 10 guests results in an increase of $500 in cost. Okay, so basically $50 a guest. Saying that, that confirms it's a linear relation. The change in the independent has to be consistent all the way with the change in the dependent. Okay, so that's linear, because sometimes you're not going to be given a graph. This one, if you notice, these are all increasing by 2. So that's consistent, but when we look at what's happening here, we're going down by 20, we're going down by 40, we're going down by 100, we're going down by what, 120, 160, going down by 260, no, sorry, 160 again. Oops. So, these are not all the same. So that's another way of telling it is not linear. Okay, so this is linear, this is not linear. Okay, so guys, so which of the following relations are linear? So we're going to look at the table of values, and we're going to do the same thing because we don't have them graphed, and nor do you want to graph them. So here, notice how these are all increasing by 5. And they don't all have to increase by the same amount, but it has to be proportional. Over here, this is increasing by 9. This is by 9. And this is by 9. So for every increase of 5 in temperature, in degrees Celsius in temperature, it's an increase of 9 in degrees Fahrenheit. Every time. So that is linear. It's a constant rate of change. So the change in T degrees Fahrenheit is constant with respect to the change in T degrees Celsius. So that's all I do. When I have a table of values, I do those little arrows to help myself. What is it increasing by each time? Okay, so this is linear. We'll read it. The change in the temperature, degrees Fahrenheit, is constant each time. It's the same each time for a constant change in the independent. Okay, let's look at the next chart. So these are all going up by 5s. So that's a constant change. This is going up by 75. Take a look here. Now this is going up by what? 225. Right away, I know it's not linear. So this is not linear. Okay? The change in the power is not constant for each each 5 increase in the current. Okay? So the change in power is not constant with respect to the constant change in current. Okay, so that's not linear. That's what you have to do. You'll guarantee you'll have some charts that you have to check. Are they linear relations, the table of values? Okay, so turn over the page. It says a new car is purchased for $24,000. Every year, the value of the car decreases by 15%. The value of the car, V, is related to time T. So is this a linear relation? So you're taking the percent of each one. You can even draw a table if you need to. Oops. So here at time 0, the value is 24,000. Now, if it decreases by 15%, that means it's worth 85% of the previous year. So you get out your calculator, 0.85 times 24,000. It's worth 20,400. Okay, it's 15% reduced the next year, but it's a percentage and it's based on the previous year's value. So now when we take here, if we take 85% of this, what do we get? If it's still in our calculator, we multiply times 0.85 and it's going to be 17,340. Notice how the change there, so going from this year to this, it reduced by what, 3,600. Now, if I take the previous year and I subtract the current year, oh, that's not what I wanted. I want the previous year. Subtract current year, and I get 3,060. Same digits, but different number. So it is not consistent. For every increase in year, the decrease is less each year because it's taking 15% of a smaller number each time. Okay, so this is not linear. Okay. Then for the next one, for a service call, an electrician charges a $75 flat rate plus $50 for each hour or part of an hour that he works. The total cost for service C is related to time T. Again, you could do a little chart if you wanted to. So this is time and cost again. So this is saying that to come out to your house, they're going to charge you $75 no matter what. Very common. Usually it's actually more than $75. So for 0, it's still going to cost you $75. $50 for each hour or part of. So for 1 hour of work, it's going to be 50 plus 75 is 125. For 2 hours of work, it's going to be 2 times 50 is 100 plus 75 is 175. So already in your head, guys, already in your head, you're doing that 2 times 50 or 3 hours times 50 or 4 hours times 50. And so each time it's increasing by 50. But you can certainly check it here. So these are increasing by 50, etc. And this is increasing by 1 for each increase in 1 hour. So this is linear. So anything, we did some in the last unit when we were talking about, say, a banquet, right? Charge for the hall plus $50 a person. That's a linear relation, okay? It's not saying if it was $50 for the first person, 55 for the second person, 60 for the third, then it's not linear, right? That's treating each guest differently. Linear is a constant rate of change. So constant treatment of each new value. Now next one is a set of ordered pairs. And again, you could put them in a chart if you needed to. I would look and see how the X values are ordered and just rearrange them if they're not in order. So if you take a look here, for X's, I'm increasing by 3 there, and here by 3. So these are in order of X values, and look at that. All the X values are increasing by 3. So that's good, because then all we have to do is see if the Y's increase by the same amount each time. So if I do that, or decrease, so in this case, 11 to 7, I'm going down by 4. 7 to 3, I'm going down by 4. 3 to negative 1, I'm going down by 4. So far, so good. All of them are the same. Okay, so this is linear. Okay, Now, sometimes we have to fill in missing values. So this tells us in question 4 that these are linear relations. So that means we have to make sure our values in the chart satisfy that. Okay, so take a look at what the x's are going up by, in this case, the independent variable. So up by 2, up by 2. Notice now, that was up by 2, but the last one is up by 3. So we have to make sure we compensate for that. Okay, because over here, 28 down to 20 is down by 8. Down by 8. Makes sense. Okay, so for every increase in 2, we're going down by 8. So we have another increase of 2 to get 6. So that means we have to go down by 8. So we'll be at 4. Okay, now, should I go down by 8 again? No. So what should I go down by? 12. Okay, because, let me explain. Walk you one. Okay, so here, if we're going up by 3, think about what it would be if we were going just up by 1. So in those groups there. So if I start at 0 and 28, and I go up by 2, I get 2 for x and 20 for y. If I were only to go up by 1, what would the value be for y? 24, halfway in between, right? So this would be 24 in here. So that means the rate of change, I'm just going to abbreviate it to ROC, equals -4. Okay? For every increase of 1 in x, we go down 4 in y. So now, if we're increasing by 3, 3 times -4 is -12. So that means we're going to go down 12, which gets us to -8. It's all about patterns and proportions. So you can fill in missing values if you need to get that. But basically, the change in y divided by the change in x gives you the overall rate of change for 1 unit increase in x. And that's, we're going to use that a lot as we go through this unit. Okay, so next one, a little bit different in that we don't have consecutive entries for y. Let's take a look at the x's, what's happening. Up by 4, up by 4, up by 4, then up by 6. Okay, so these first 3, or sorry, I guess first 4 rows will have entries with the same y value. What's that, Sam? No, I gotta go from 4 and subtract 12. So that would be -8. You good? Yeah. Okay, so here we're going up by the same amount. So notice here that I have to fill in this value. Who can tell me what they think it would be? Because this is going from all the way here is going up 26 units. Okay, so what did you increase by? 13, right? Half of 26. So here, this whole thing going from here to here, we know is going up by 26. And so halfway would be going up by 13. Or you can take the average of those two numbers. No matter what, you get 7. Okay, so then check it out. Is 7 plus 13 20? Sure is. So you can always check your answer. So that means the next row, if we're going up by 4 again, I got to go up by 13. Same value. All right. Now, the next one is going up by 6. So you could say the rate of change is 13 divided by 4, but that's a fraction, kind of yucky, okay? But you could, or think about what would be in between here. So if we went up by 4 again, that would be 28, and 13 in that would be 46. And then what would we go up for y for the next 2? Not going up by 4, but going up by 2. Yeah, half of 13. Right, so here we can go up by 13 there. And then from there, we're going to go up 13 over 2 because it is half, it's 2 more units. So that's 6.5. So that value would be 52.5. Rate of change. Okay. So extend your chart if you need to. It's all proportions. Okay. Next one is a set of ordered pairs. So you want to, if you want to set it out as a chart, a table, then do it. So we'll have -3. We don't know what the y value is. We have 0, 7. We have +3. We don't know what the y value is. We have +6. We don't know what the y value is. And then we have 9 and 31. Okay, so what's happening here? We are increasing by 3 each row. This is an easy one. Guys, can you stop? Okay, so those are all consistent. So let's look. The only 2 y values we have are these ones. So if you're going from 7 to 31, what's that? Up 24. Okay, but now there's 2 lines in between. So you have to think about, rather than dividing 24 by 2, we have to divide it by 3 so that we get this plus this plus this. So what's 24 divided by 3? 8. So if we go 7 plus 8 is 15, plus 8 is 23, plus 8 is 31. Always check, make sure you keep going. So if we keep adding 8 as we go down, then going upwards, we have to subtract 8. So this would then be -1. Okay. So let me put that in here, -1, 0, 7, 3, 15, 6, 23, and 9, 31. Okay, so then we'll get to the official definition of rate of change on the top of the next page. So the rate of change of a linear relation is given by the change in the dependent variable, whatever it is. Usually that's y. Could be cost, it could be temperature, depends on the situation, but it's dependent over the change of independent. So for each linear relation, determine the rate of change. Include units with your answer and what it represents in words. Okay, so here the rate of change, we'll just use that abbreviation, equals the change in cost divided by the change in number of guests. We just look at what's the dependent and what's the independent? Yep. Okay. So then choose these. You can only find the rate of change if it's a line, linear relation. So you don't have to do it for all points. You want to find 2 points. I always take the one that might have a 0 in it. So I'm going to compare these 2 points. So the change in cost. So if I'm going from 400 to 900. So I'm going up to that point and then across. So 400 to 900 is 500. And then that's for 10 guests. And we already figured this out. This graph was one of those first ones. And I already said the cost of each guest was $50. We figured that out. And so that's the rate of change. So then put in units. Okay, so it's $50 per guest. That's the rate of change. Sometimes when it's not an application question, we just call it the slope of the line, how steep it is. But for applications, we call it the rate of change. Okay, so next one. This is rate of change equals change in altitude divided by change in time. Okay, choose 2 points. So we're starting at 1,000. The next point's starting at 10,000. The next point is 8,000. So we're actually going down 2,000. So we use a negative symbol. Because that graph is going down and to the right, so it actually has a negative rate of change or negative slope. Okay, and then the difference in the time there, that goes to 4 minutes. So this would be divided by 4. And so it would be negative 500, and that would be meters per minute. Because you choose 2 points on the graph, and you're going from 10,000 down to 8,000. Always go from left to right on the graph. Okay. So now we don't have a graph, we have a table of values. And it says the distance driven in kilometers, volume of gas in liters. So basically how much volume you're using. So the rate of change is the change in volume of gas divided by change in distance. So it's really going to give you, if you talk about mileage in terms of gas efficiency with a car, they actually post it. When you go look at a car in a dealership lot, they'll give you the rate of change. How many liters of gas will be used for driving 100 kilometers or something. I don't know what their basis is. I think 100 kilometers they put it comparative to. We'll just do it per kilometer. So in this case, I'm going to go from here to here. So it's using, what's that, 15 for every 100 kilometers. Now that can reduce to negative 3 over 20. Okay. Sometimes they'll give the decimal form of this. Certainly when you're going to buy a vehicle. So if we did that, that would be 0.015, right? Yeah. I did, yeah. You should always simplify a fraction. Yep. Oh, just a sec. Yep, that's right. Oh yeah, because it's 15 over 100, so of course it's 0.15. Okay, so yeah. If it asked you to. If it asked you to. Otherwise you don't. Yeah, if it's just asked for the rate of change, you don't have to state what it is. But you will have to use units. Yeah. Okay, so sometimes if you go traveling, they actually charge you for internet use. So in this case, the rate of change is dollar, the cost, change in cost. Change in hours. Okay, so change in cost, we're going up again. It's linear, so we're going up by the same amount because the hours of use are going up by the same amount. And so that's 4 over 2. And so that reduces to 2, and that's going to be $2 per hour. Okay, so $4 2 hours, and then you reduce that to $2 per hour.
You're doing changing cost over changing hours?
Hours.
Hours.
H-O-U-R-S. Well, just look at the chart. Okay, so those were tables. So we've done graphs, we've done tables, and now this is an equation. Notice how it's in function notation form. So cost as a function of n, number of guests, is 25n plus 200. We've done some similar like this. So what's the rate of change? Do we even need a chart? Who can tell me what the rate of change? As we increase by 1 guest, how much does the cost increase by? 25. Right. So you can test it out. If you want to do C of 0, that's 200. C of 1 is 25 plus 200, which is 225. So the rate of change is going to be 25 over 1, which is $25 per person, per guest. Okay. Is that right? Okay. So this one, m equals 50 minus 1.3 t. M is the mass in pounds and t is the time in seconds. So looking at that, comparing to the last one, so a linear function always has no exponents on the variables, okay? Notice how our rate of change here was the coefficient of n. So what's your instinct about the rate of change in part F? Based on what I just said. What do you think the rate of change is? 1.3 with the negative. So it's going to decrease by 1.3 each time. So we could test it out if we went I'll change it to function notation. So if I go m of t, this is why function notation is so nice. because then it is easy to tell what you're substituting in. So if I go m of 0, I get 50. If I go m of 1, I get, wait till it catches up. I get 50 minus 1.3, which is 48.7. And so you can tell the rate of change is the difference, which is negative 1.3 over 1, which is negative 1.3. Now, what units is this? Mass is in pounds. Per second. Okay. All right. That one. So one more question, a big one on the back. Actually, I think we'll stop here. Okay, so looking at question 6, a plane begins to land at Calgary Airport from an altitude of 8,000 at a rate of 1,000 per minute. Complete the table. So it starts at an altitude of 8,000, and then after 1 minute, it'll be 1,000 less than that, so 7,000. So we'll do this for each minute. And then this will go down by 1,000 each time. Okay, so then sketch the graph. So this will be time in minutes. And this will be altitude. To draw on the side, and that is in meters. And then the horizontal, I'll label that as T, and vertical as A. And so plot them. So 0, 8,000, 1, 7,000, 2, 6. So you'll notice they form a straight line. So this is a linear relation. Now in real life, when the plane lands, it's going to curve, sort of go a little bit gradual. This looks like it's going to just basically comp onto the ground there. So it would be gradual, but this is a good approximation. And so if you think about it, we can join these up with a line because a plane doesn't jump between each minute. It's not magic, right? So it's a continuous descent. So let me just fix that a little bit. So it says write the equation in function notation. So our dependent is A in terms of time. And what's our rate of change here? Well, for every change in 1 minute, the altitude decreases by 1,000. So our rate of change is negative 1,000 meters per minute. So that's what we always multiply our independent variable by. Okay, and then we have to think about what if there's a constant term as well. So here at time 0, the altitude is 8,000. So if I put 0 in for t, that term goes to 0. So I've got to have 8,000. So that vertical asymptote is always the constant term. Rate of change, I've already done that. Whether it's discrete or continuous, I already did. It's continuous as a plane descends continuously. Let's see if my computer will catch up. Doesn't look like it. Okay, so my computer caught up. Plane descends continuously. It can't skip from 1 minute to the next. Domain and range. So it doesn't say what form to put it in. If I put it in interval, so look back, your time goes from 0 to 8, and your altitude goes from 0 to 8,000. So this would be from 0 to 8, and the range from 0 to 8,000. If we do it in set builder, then we're dealing with time. So from 0 to 8. And range is A, going from 0 to 8,000. Horizontal intercept. Well, where does it touch the horizontal axis? There at 8. So the coordinates of that point are 8, 0, and that's the time it takes to land. Okay, or I guess descend and then land, because really this graph started at the point where it started to descend, and then so I'll put after starting its descent. And then the vertical intercept is 0, 8,000 in round brackets. And that's the height, the initial height of the plane when it starts to descend. Okay, then use your equation to determine the height after 3 minutes and 45 seconds. So we have to get this all in minutes. So remember, there's 60 seconds in a minute. So we're going to divide this by 60. So this will be 3.75. Okay, we divided by 60. So now we're going to go A of 3.75 equals, and then we substitute it into the equation. Okay, and then simplify that. So negative 1,000 times 3.75 is going to be negative 3,750. And then when we add those together, what will we get? 4,250. And we can check our graph to see if that makes sense. So if I go back up here, 3 3/4 up here looks a little more than 4,000, which it is. Okay, then you use your equation to determine the time in minutes and seconds when the plane reaches a height of 1,100. So now that's our A value. So 1,100 equals negative 1,000 t plus 8,000. So bring the 8,000 to the left. And so what that's going to be negative 6,900. then divide by -1000. So T equals, so here that when we divide is going to be positive 6.9, and that's minutes. Okay, so that's all in minutes. It's a decimal. So now it says in minutes and seconds. So the whole number is going to be the number of full minutes. And then we have to figure out what 0.9 of a minute is in seconds. So 0.9 minutes, if I multiply by 60 seconds in a minute, that will give me my number of seconds, right? If you think about unit analysis, the minutes divide out, and so 0.9 times 60 is going to be 54 seconds. And so that's the answer in minutes and seconds. So if we take a look on our graph at 1100, approximately, then, oops, what did I just do? 1100 just above here, so we go across, and it's going to be a little less than 7 minutes, and this is a little less than 7 minutes. Okay, 6 seconds short. All right, so then we're done the lesson, and you can start the practice.